Hi, welcome back to my channel. Well, in this video we'll try to learn how we can fit a curve or how we can fit a equation or a model by means of a very important add-in which is available in MS Excel, that is known as solver. Say for example, for that we need to go click on this data, and once we click on this data we used to get this solver just on the right side of this spreadsheet that is known as solver. So in this video we'll first start with the basic simple linear regression equation. For that we have taken a data set of 100 observations, or we can say the 100 pine trees, utilizing two variables, height and diameter, and the equation we need to, where we are interested to fit, is this basic simple linear regression. We are starting with the simple linear regression, height versus diameter. And since in one of my videos I have given a detailed procedure about how we can fit a simple linear regression or a multiple regression by means of a data analysis tool pack, very quickly I will click on this data analysis, then we will click on this regression. Then we need to first highlight this our dependent variables. In this case height is my dependent variable. Then we need to choose this our explanatory variables. This is diameter. Then labels, we'll click on this labels because already we have given the name to both the variables. Then residuals are very important. Then we will click on this output. So suppose I want my output to be displayed here, the results of my output here. Then we'll click on this. Okay, so this is the simplest way, or a very quick way, to fit a simple regression model by means of data analysis tool pack. But the problem arises when we have to fit, say suppose an equation between height and diameter which is non-linear in nature. This data analysis tool pack is not going to work at that time. So first we will start with a linear model by means of which we need to execute or set an equation or a relationship between diameter and by means of solver. So we will start with the procedure first. First we need to calculate this predicted height utilizing this equation. For that we will simply write is equal to, then before is equal to, the one thing is very important whenever we are interested to fit a model which includes some parameters, we need to give some initial values to the parameters. So we always start with the 1 and 1. So we are giving the initial values of 1 and 1 for this intercept as well as this regression coefficient in this equation. Since this is a simple case, this is the simplest case which I am starting with. So this is the traditional way to fit an equation. We will write is equal to within this cell. Then the equation is a plus b into diameter, so a, then plus this is b, that is the coefficient, then multiply by, and I will start with a bracket. This is my diameter, and close the back bracket. But important thing is that we need to put the dollar signs here. Suppose if we will not put the dollar signs here, we will press on this enter, see what will happen. I will double click here, see the rest of the data points are not regressed by means of this equation. For that we need to put the dollar signs before these alphabets, which is actually, which gives the position of this data point within a cell where it is. Then again we will double click on this, so we have got this. Now the important thing in regression analysis is that we have two variables. Actually it is height is equal to a plus b, and then diameter, and there is also an error term involved in it. So we need to get that error term also, or we can say the residuals, which are nothing, which are the deviations or the difference between the actual value and the predicted value. So we will simply write is equal to, then the actual height minus the predicted height raised to the power 2. Then we will press on this enter. Then we will double click on this. So we have got the deviation sum of squares, which deviations are nothing, these are the errors. But we need another important thing, that means we need to get the sum of this. So we will simply go to this home, then we will click on this. So this is the sum or we can say the error sum of squares. But if you will remember, the theoretical aspect of the regression analysis is based on a very important principle, that is known as the principle of least square, which says we have to choose those values of these parameters which will minimize this difference, which is actually the difference between the actual height and the predicted height. For that, what we need to do, we need to simply go to this data, then we will click on this solver here, then we need to set our objective function here. We need to set our objective, that is our the sum of squares here, which is based on this deviation. Then what we need to do, we need to minimize it by changing the values of what, which are our parameters here. Then we will click on this solve, then we will keep this solver, then click on this OK. So we have got the value for intercept and the value of our regression coefficient, which you can clearly see, which is similar to the value which is we have just got from this data analysis tool pack. That is 2.73 is the intercept here, same is the case as here, and the regression coefficient is 0.62. That means with an increase of 1 centimeter in diameter, the height increases by 0.62 meters, or whatever the measurements of units you have taken. The another important thing is that we have also got this error sum of square, or sum of square due to the residual or residual sum of square, that is 12.56. I will simply copy this thing and I will put it here. I will put on this like this. Again, I will copy this because this is based on a formula. Then I will click on this, right click on the spatial and values. Now you can see this is the sum of square due to residual or residual sum of square, or we can say this error sum of square. It is 12.56, which is based which we have just calculated from this solver, and which is similar to this. So we need to get this sum of square due to regression or due to the model. For that, what we need to do, we need to first calculate the average of this actual dependent variable, average of these observations. So we will click on this, then we will go to this home here. Very quickly click on this. So we have got the average. Now in order to get the regression sum of square due to regression, we will simply write is equal to, then we will start with the bracket, then we will click on this minus this predicted height, again raised to the power 2, then we will click on the center. Then again, the important thing is that we need to put this average value within these dollar signs. Click on this, double click on this, then what we have to do, we'll simply get the sum of this. Okay, this is the auto sum, and you can see it is 11,11330.75. I will put this here, paste spatial again, click on these values. Now you can verify it from this, it is 11,330.89. So in order to get the total sum of square, we will simply write is equal to, then sum these two. So we have got the total sum of square, which is similar to the values which we have got from this data analysis tool pack. Then we need to get this r squared, that is coefficient of determination, which is nothing, which is 1 minus the ratio of the sum of square due to error divided by the total sum of square, which is equal to 1 minus within these brackets. So I will put this residual sum of square divided by total sum of square, then I will press on this enter. So it is 0.90. It is similar to this, that is 0.90. So this diameter is able to capture the 90% of the variation in the height alone. Only 10% of the variation remains in the error. Now we need to get the adjusted r square, although which is not usually used whenever we are dealing with just one explanator value. It is actually a selection criteria which is used to evaluate different models with different parameters, and it is always adjusted with it. As we will get this is equal to 1 minus, okay, I will put this in bracket, then another, that is residual sum square minus 98. The reason is that 100 number of observations and minus k, two parameters a and b, which is equal to 100 minus 2 is 98. Then again we'll keep this whole divided by total sum of squares is this, divided by n minus 1 is 99. Then we'll keep this, then again another bracket, and click on this enter, which is 0.899, which is similar to the value which we have got from this data analysis tool pack. The mean square is nothing, it is the ratio of 2 residual sum of square whole divided by 98 n minus k, and its square root is always equal to the root mean square. So we have got root means all these selection criteria, and you can see the predicted height which is based on data analysis tool pack is similar to this 10.3 to 11.85. You can see 10.3 to 11.87. So the thing is clear that we can fit any linear or non-linear model by means of solver, which is a problem in case of data analysis tool pack. So this is a very important add-in which is available in MS Excel. We can make a simple XY plot also here. For that we need to first highlight all these three things, including diameter, actual height and predicted height. Then we will go to these plots, then click on these charts, then we will go to this XY plot, then click on this OK. And you can see the R square was almost 98 to 99%. You can see it was 90%, so you are having a predicted height which is totally crossing across these observed values, so it is almost completely fitting the underlying relationship that exists between diameter and height. So in next video we'll try to fit a non-linear model utilizing this add-in that is solver. Hope you will like this video. Thank you very much.